All right. G'day, everyone. My name's Wright. I work at DBird. I'm also at UWA doing a PhD under Nick Callow. I'm here today to talk about a Python library that we pushed out a couple of months ago called CloudS2Mask for Sentinel 2 cloud and cloud shadow masking. So I guess you'd probably mostly be aware Sentinel 2, the constellation has been up since started in 2015. 10 meter resolution of the RGB and near-infrared bands with a 5-day revisit since they put the second one up a few years ago. It's really useful, especially for a lot of the things that we do at DBird with like land condition monitoring and like crop monitoring and whatnot. But it has a bit of an issue, and that is clouds. So a lot of the imagery, I think it's like 60% of the world is covered by cloud at any point in time. So a lot of the images that you get, a lot of the scenes that you get have some percentage of cloud in them. And it's really difficult to deal with. So there's been a few solutions that have been out for a while. You've got F-Mask, which was adapted a few years ago to work with Sentinel. I think version 3 was the first one that worked with Sentinel, and then more recently there's been version 4. And S2cloudless is another popular one, which just identifies clouds, and then you can also like extract shadows using like sun azimuth and like projecting it out and then finding the dark stuff. But it's a bit of a pain to do that, and F-Mask is like actually surprisingly good, but it really struggles with thin cloud and also detection over urban environments. So this was, I guess the reason this is difficult is because of the bands that Sentinel picks up, the spectral bands. So Landsat has it a little bit easy because it's got thermal bands and you can pick up clouds just because they're freaking cold. And then from that, that informs your projection of shadows, and that helps out a lot. Sentinel, we don't have the luxury of thermal bands, so you need to be a bit more clever. So there's been a few somewhat recent developments. Like 3 or 4 years ago, Kappa Mask came out, which was a deep learning segmentation model based on, they collected several thousand, 5,000 or so, training data patches to train a deep learning UNet style model on. So what that involves is collecting little chunks of Sentinel imagery like this and then manually going in and saying this is cloud, this is like somewhat see-through cloud, this is shadow. And you just train a model up on that on all 13 bands and then just kind of hope for the best. And it actually does work pretty well. But it's really difficult to collect enough of this data. At the end of last year, CloudS2 came out, which is an amazing piece of work. They collected 10,000 of these high-quality masks. And they trained up a model which they called UNet Mob v2, which is a UNet-style model with a MobileNet v2 backbone. And it works pretty damn well. You can see the graphs on the top right there, which are nicked from their paper. The further to the right that most of the lump of data is, the better it is. So the one at the very top is the human label. So that's like as good as you're ever going to get. The next one down is their model, this UNet Mob v2 thing. And then it just slowly gets worse as you go down. You can see the Kappa Mask is pretty good, F-Mask is pretty good, S2cloudless is pretty good, and then it kind of trails off. But using deep learning has a few issues. There's just a few pain points. So primarily, it comes down to, so Sentinel scenes are kind of big. They're like, you've got 13 channels, and it's like 10,000 by 10,000 pixels. And pushing that through a deep learning model on a GPU, you just run out of RAM. So what you have to do is cut up the scene into little overlapping patches, and then run those through your model in batches of like 8 or whatever. But then you've got problems of like, you've got all these predictions of patches that overlap with one another and you need to like reintegrate them somehow. And like you can like average them and that kind of works, but you end up with weirdnesses like you've got in the top right there. These, the red arrows are indicating areas where you've got like straight lines, and as we all know, straight lines don't exist in nature. So something weird is going on there, and it's just where one prediction patch has been merged with another, and they just, like, it just doesn't integrate very nicely. And that is kind of because of this thing on the bottom right. So that shows the spatial accuracy of a UNet style model with an input size of 128 by 128. And as you can see, in the middle, it's great, and it slowly gets worse towards the edges, and the corners are like significantly worse than the middle. And that's just because of a lack of context, right? So these models are rolling convolutions over an image to pick up like the texture. And as you get to the corners, you've just got pixels that you can't see anymore because the model only gets to see this little patch. And it's worse in the corners because you can't see pixels in two directions. So the other part is that these models are freaking slow to run. Even on like high-end consumer hardware, you can be looking at like a minute or two per scene. And when you've got a few thousand scenes to process, it just doesn't scale particularly well. Especially when things like F-Mask, if you're running it at like 20 meter res, it takes like 20-ish seconds, which is a lot nicer. So here are some of the solutions we came up with. Firstly, you've got patch location optimization. So the conventional way of cutting up a scene is you just grid the whole thing and they all overlap with one another, so you can like remove the very worst predictions on the edge and then just smush it all back together, which like works, sure. A slightly better way to do it is to offset every second grid horizontally by half the width. So then you've got the worst prediction of like this one being in the center of the one above. And what that results in is this kind of confidence array where you're removing those very worst like combinations. Like each prediction on one of these, the worst bit are these corners, and you've got all four corners overlapping in the same spot. So if you can shift this horizontally, you're then getting the worst predictions in the middle of the one above, and the one above has better predictions, so you just use those instead. And that's what this diagram is trying to show. By using this approach, you can get rid of the very worst predictions and just kind of shuffle it all up. So you get an extra like just smidge of accuracy, and it just helps reintegrate those patches. Another one is quite often these libraries will process like no data regions of a scene. So they'll get a scene that looks like this, and they'll just put a grid over the whole thing, chop out all these no data regions, and run through the model, and then it's like, oh, well, you know, it's kind of pointless. So in our approach, we just don't process any of these green areas, and the red ones, like this one here has like 90% no data. So what we do is we just like push it up, and for this one we push it up and in as much as we can so that it covers its initial data area and then additional area as well. So that doesn't make us any faster, but it just means we get free overlap. So this is what the kind of inference pipeline looks like. So we trained our own model based on a combination of different data sets. We just kind of smushed them all together into, I think we had like 50,000 images to train on. And we chose a model which was particularly optimized for GPU compute. So it ran really fast on the GPU. And then, so the pipeline sort of looks like this. So the CPU reads in a scene, chops up the tiles with this offset approach, ships that off to the GPU, you make your predictions, we then generate a gradient array, which is like an idealized version of the confidence array that I showed you earlier, where it's like worse towards the edges. We enforce that on the predictions, and then we merge it back together. And what that does is it downweights these kind of low quality predictions on the edge, and then we just take an average of all of those arrays, and you end up with this nice merge prediction over an entire scene with no straight lines. And there's a few advantages of kind of this pipeline kind of approach is if you're processing more than one scene, this bit of it is CPU bound, this bit of it is GPU bound, and this bit of it is CPU bound. So if you're doing more than one scene, you can start one, and as soon as you get to this point of the GPU being taxed, you can start the next scene and tile up the next scene. And then as soon as this one is done, you ship that off into another thread, and it merges it all and saves it. And then the one that you've already prepped goes straight into the model. So that GPU is just completely getting hammered all the time, and the CPU is just chucking data as fast as it can. And we end up with some pretty crazy results. So we trained our model at 10 meter res, but also at 20 meter res, because clouds are so big and fluffy, it doesn't really matter if you're running 20 meters or 10 meters. Like you may as well run it at 20, everything runs 4 times faster, and the output is like pretty much the same. The accuracy difference is like insignificant. So we can run our 20 meter model on a single workstation. It takes 2.2 seconds per scene. We can run our 10 meter version. It takes 7 seconds a scene. F-Mask again, running at 20 meter res takes 17 seconds. And the deep learning ones take like a minute or 2. So you can really churn through the data. That's running on a Ryzen 5950X, so a high-end CPU from a couple of years ago, and a RTX 4090 GPU. So it's like like an $8,000 workstation. And the actual usage of it is pretty straightforward. So you just pip install it, tell it where your data is, tell it where you want your mask to go, set up, just input these variables here, tell it to go, and it just does the whole thing for you. Hopefully, we can actually run that live. So this is running locally on a M2 MacBook Air, so not the most powerful computer in the world, but you know, it's all right. And one nice thing is the back end of it is all PyTorch, which means we can use the MPS GPU in these MacBooks. So it runs fast on, like if you actually want to run it in production. Oh, you can't see that. 1 second. And show. Which way are we going? This way. Cool. So let's just reset that and run it from the top. Okay, cool. So we're just importing the libraries, telling it where my single scene is, and then running inference. So right now it's just opened up the data at 20 meter res, converted it into tiles. It's now running on the MPS module on the MacBook. And in another 10 seconds, we should be done. So yeah, because it's using PyTorch as the back end, it'll run fast on newish Macs, but really fast on CUDA devices. So anything with an NVIDIA GPU from the last couple of years. And then we're done. So if we open up this, so the output is, it makes for convenience, it outputs a VRT of the Sentinel image, so we can view it, and then a geotiff of the mask. Ta-da! Yeah, so it generally works pretty well. And yeah, it's just pip install CloudS2Mask and off you go. I think that's about it. Oh, funding sources. So yeah, Department of Ag, the Future Drought Fund, and the Australian Government Research Training Program. And yeah, that's it. Thank you.
Thanks, Nick. That's cool. Any questions for Nick about that?
If you come across any solutions that are using, in particular for the Sentinel stuff, if you're revisiting every 5 days, you've got a whole bunch of different shots.
Yeah. Yeah.
Are there solutions that are competitive that are using the historical versions of differences that way?
Yeah, so the Marja processor has been out for quite a while, and that does like a multi-temporal approach. It's not as accurate as doing ML approaches. Doing like a multi-temporal deep learning approach would be probably even better again, but you just need so much more data. It's so convenient when I've just got like one file. I don't need to download a whole archive to kind of process it. It's much more convenient this way. Google put out a paper that I think like in the last month or two, where it was completely unsupervised and they just ran through a colossal amount of data, and they had pretty good results. I haven't benchmarked it against this. They were comparing with S2cloudless and they seem to improve it a bit, but yeah, I'm not sure how that compares. But yeah, it's like a decent approach, and conceptually it should be better, yeah.
Yeah, it's cool to hear that this approach, just using it is as good and like more practical.
Yeah, for sure. Anything else?
All right. Yeah, thanks again, Nick. That's great.